1060 Intro to Trig CBE 2 review. So we'll be going over simplifying trigonometric expressions using trig identities, inverse trig functions, and degrees to radians. Just a refresher, here's the unit circle. You guys should probably have that memorized by now. If not, see our other videos. Here are some trig identities that you guys use to simplify the trigonometric expressions. There's some more trig identities. Cool. And off to problem 1. So, okay, yeah. So this one we're gonna need to use our power reduction. No. So first thing, looking at this, we can factor out a cosine squared and a sine squared, so we can rewrite it like this. Messed up already. That's actually a 3. And then we can rewrite it, and this becomes sine squared plus cosine squared. And if you should remember, sine squared of x plus cosine squared of x equals 1. So the inside just goes to 1. And so this actually just equals cosine squared sine cubed.
Okay, so here we have some more trig identities that we're going to use for some problems later. Okay, so to simplify this expression. So first thing I'm looking at is we have a cosine of 2x, but we probably want that to just have an x. So one thing we can use is one of our half angle identities that was on this previous slide. So I'm going to use that cosine of 2x equals cosine squared of x minus sine squared. So we can write this cosine of 2x as that. And plus sine squared of x. And we have minus sine squared plus sine squared. So that cancels, and then we just have cosine squared of x.
Cool. On to problem 3. So this one we're given the angles and where the angles lie. So we're gonna have to use the sum product, I believe it's called, identity, which basically states that sine of two things in addition, so sine of a plus, this is a plus sign, plus b equals sine of a cosine of b. I gotta take beta, but it's fine. Plus sine of b and cosine of a. Okay, so here we're given that sine of a equals 2/5. So we know that if we draw a triangle, and remember that sine is opposite over hypotenuse. We know that this is a 2. The hypotenuse is therefore a 5. So if we solve for the other side, because we're going to need it for the cosine, that it becomes root 21. Now we know that alpha is between pi and pi over 2. So it's in the second quadrant. We know that all the cosines in this quadrant are negative. So I'm going to make that a negative root 21. And then we'll have to draw our second triangle here. That triangle. Where the second triangle of beta, switch color really. Okay. And we know that this is negative 2 over 7. So that's negative 2 to 7, just like we did. And then we're going to solve for the other half. And it is root 45. We know that beta is in the fourth quadrant and all the cosines are positive and the sines are negative. So we did get that triangle right. Now we just plug it into our formula here. So sine of A or sine of alpha is 2/5 times the cosine of beta, which is root 45 over 7 plus the sine of beta, which is negative 2/7 times the cosine of alpha, which is negative root 21 over 5. And when you multiply all that out, it simplifies to 2 root 45 plus 2 root 21 over 35.
Okay, our next problem is, again, we want to simplify this, but we want to write it as an algebraic expression. So without any sines or cosines in it. So the first thing is we have a sine function with something plus something inside of it. So I think we want to use the sine sum identity. And that is that the sine of the first thing, which is the arctangent, times cosine of the second thing, which is arcsine, plus cosine of the first thing, which again is arctangent, times sine of the second thing, which is arcsine. And if we look at this, we have a sine and then an arcsine. So these kind of get rid of each other and just leave us with an x right here. Okay. The next thing we want to do is try to simplify some of these. We have sine of arctangent, which is not very nice. So we remember tangent of theta is opposite over adjacent. So that means arctangent takes in opposite over adjacent and gives us theta. So I like to draw a little triangle just to think about it. We have, so arctangent, it's taking an x, which is opposite over adjacent. So we can kind of just write that as x over 1. And here's our theta. Okay. So arctangent, it takes in our x over 1 and gives us our theta. Okay. So we also want to find this other side. So the way we can do that is by using just the Pythagorean theorem. So we know that x squared plus 1 squared equals our third side squared. And if we take the square root of that, we get square root of x squared plus 1 squared. And because 1 squared is just 1, we can write that as square root of x squared plus 1. Okay. So we want to find the sine of our inverse tangent. So sine is opposite over hypotenuse. So our opposite here is x, and our hypotenuse is x squared plus 1. So our sine of this, and remember inverse tangent is our theta, so sine of the inverse tangent is the same as sine of theta. So that will give us opposite, which is x, or hypotenuse, which is x squared plus 1. And then we have cosine times sine inverse, which we'll take care of in a second, plus, we already did this for inverse tangent, so let's just do the cosine one now. Cosine is our adjacent over hypotenuse. So here our adjacent is 1, our hypotenuse is square root of x squared plus 1. So we have 1 over square root of x squared plus 1, and then we still have that x. Okay, now let's do the same thing to figure out this arc sine. Draw another little triangle. Arc sine is our angle. And then sine takes an opposite over hypotenuse. Well, sine gives us that, so arc sine takes it in. And it looks like arc sine is taking in x again. So opposite over hypotenuse, the opposite is x over 1. Okay, and then using the Pythagorean theorem again, we have 1 squared plus x squared. It's our missing side squared plus x squared equals 1 squared. So we can do our missing side squared equals 1 squared minus x squared. Then take the square root of everything to get our missing side equals 1 minus x squared. The same thing with the 1, because 1 squared is 1. We can just write 1. Okay, so that's our missing side. Goes right there. So our cosine of that, cosine is adjacent over hypotenuse. So I'm just rewriting this stuff from before. And then adjacent is the thing we just found. 1 minus x squared over hypotenuse is 1. And then plus square root of x squared plus 1 times x. Okay, then we can simplify this a little more just using some algebra. We get x times 1 minus x squared over square root of x squared plus 1 plus x over x squared plus 1. And this is a common denominator, so we can write it all as one fraction. Plus x over square root of x squared plus 1.
Cool. Okay. So this question is asking us using identities and the knowledge of special angles. So right there, you should all be thinking unit circle. Because those are our air quotes special angles. Oh, it says it right here too. On the unit circle, to determine an exact value of cosine of 157.5. So we want to think, how can I make that angle a unit circle value? And it just so happens that 157 0.5 is equal to 315 over 2. 315 is on unit circle. UC for short. Check mark. So then we can now apply our half angle identity, which states that cosine of theta over 2 is equal to the square root of 1 minus cosine theta over 2. 1 plus cosine theta over 2. So yeah, so we can just plug this in, and we're going to state theta equals 315. So then the cosine of 315 over 2, which is equal to the cosine of 157.5 over, not over anything. Oh. Is, I just did it again. Anyways, just underline that to the side. The square root of 1 plus, then the cosine of 315 is root 2 over 2 over 2. And you can keep simplifying that further, but like you can rationalize it and everything, but this is a good enough answer for most professors. Since those are some slides.
Yeah.
So.
Okay, so here we have some information about alpha and beta. We want to find, oh, not alpha, just beta. Okay, and we want to find sine of beta over 2. So this to me looks like we're going to have to use one of our half angle identities. So because we know sine of beta, but not of sine of beta over 2. So because this is double this one, our sine beta is double beta over 2, we can use our doubles identities. So I'm actually going to use the cosine identity here, one that says cosine of 2 theta equals 1 minus 2 sine squared of theta. In this case, because beta is the double, it's just cosine of beta equals 1 minus 2 sine squared of beta over 2. Okay, so now we have a beta over 2, which is what we're looking for. So we want to solve for that. Okay, so I'm going to subtract this 1 over, get cosine of beta minus 1 equals negative 2 sine squared beta over 2. Okay, and then I'm going to divide both sides by negative 2. Because we're dividing by a negative, we can just flip all these signs to get negative cosine of beta plus 1 over 2 equals sine squared beta over 2. Okay, we're close. Now we just have to get rid of this squared, so we can square root this to get sine of beta over 2 equals the square root, and remember the plus or minus square root of, I'm going to switch the order of this 1 and cosine, but it's still the same thing, just to get 1 minus cosine of beta over 2. Okay, now what should we do? We still have this cosine in here, which is a little annoying. So what can we do about that? Well, we know stuff about sine. We have cosine squared plus sine squared equals 1. So what if we do cosine squared equals 1 minus sine squared? Then we need just a regular cosine, so we're going to take the square root of that to get cosine equals the square root of 1 minus sine squared. Okay, and now we should add little angles here. Oh, I guess we're working with betas. Okay, so we have sine of beta is negative 2/3. So sine squared of beta equals square root of a negative makes a positive, 4/9. Okay, so now we have cosine of beta equals the square root of 1 minus 4/9. Then we can simplify that a little more. Cosine of beta equals square root of 5/9. And 9 is a perfect square, so we can pull that out. To get cosine of beta, it's the square root of 3. Okay, so now we have a nice number that doesn't have a cosine. So we have sine of beta over 2 equals the square root of 1 minus square root of 5/3/2. Okay. Oh, there's one thing I forgot. We have this. So this means we're not in the first quadrant. If we go between pi and 3 pi halves, we're in this quadrant right here, quadrant 3. And here cosine is negative. So we actually have a negative. But since we're subtracting a negative, it's plus. Okay, if we want to simplify this more, we can multiply everything by 3 just to get rid of this double fraction to get 3 plus square root of 5/6.
All right, cool. Problem set. So here we have cosine of x times sine squared of x. And it just wants us to reduce it to an expression where there's only one trigonometric factor, and that each trigonometric factor is only raised to the first power. So there's going to be two identities that we're going to need here. And I'll list the first one. So sine is our power reduction property, which states that sine squared x equals 1 minus cosine of 2x over 2. So here we can sub that one in, and we get cosine times 1 minus cosine of... No, I need to be better. Sorry. Keep dropping all my... I keep doing that. Keep dropping all my sines and x's and stuff. Alright. So cosine of x times 1 minus cosine of 2x over 2 is equivalent to cosine of x over 2 minus cosine of x times cosine of 2x over 2. Okay. Now we have a product to sum identity here, which we can use the identity of cosine of alpha times cosine of beta equals 1/2 cosine of alpha minus beta plus cosine of alpha plus beta. Okay. Then if we plug that in right there, we end up with the expression of cosine of x over 2 minus 1/4 cosine of, I just got that 1/4 from the 1/2 times the 1/2 right there. So we pull that 1/4 out and get cosine of x minus 2x plus cosine of x plus 2x here. So then, multiplying all that out, you'll get cosine of x over 2 minus cosine negative x over 4 minus cosine 3x over 4, which equates to cosine. Wait, remind me, can I take the negative out of the x? Yeah.
Yeah, there's a
That's right, that's right.
negatives, but with cosine it just deletes it pretty much.
Exactly. Okay, so even though this technically is a negative x, because cosine is, I think it's a symmetric function, right?
Yeah, I think they call it like an odd function.
Or because cosine's is it an even function?
Yeah.
Because cosine is even, that means that the negative will always equal the positive. And so we take that x out, then we just get cosine of x over, minus cosine of 3x over 4. And that is our answer.
Okay, this one is a little different. So we want to find a 4 decimal place approximation for any solutions to this equation. Okay, so first as in algebra, we want to get our x by itself. So I'm going to subtract 4 from both sides. So 5 sine x equals minus 4. Okay, now I'm going to divide both by 5 to get sine of x equals negative 4/5. We want to remember that sine is negative, because that will help us later. Okay, now how do we get rid of a sine? We want to do the inverse of sine. So we can do inverse sine to both sides to get rid of that, to get x equals the arc sine of negative 4/5. And here we can just do the positive one and then make sure we remember that sign is negative to figure out where our solution is. So when we plug inverse sine of 4/5 into our calculator, we get that it is about 0.9273. Okay, now we need to figure out, because our sign is negative, where that is in our unit circle. Okay, so sign is negative in quadrant 3 and 4. So this answer is somewhere over here. It's positive. So what we can do is, for the one in quadrant 3, we can add a pi, which is half of our circle, then add our positive solution. So we get pi plus 0.9273. And then this, again, we're rounding, so it's just approximately 4.0689. Okay, now our quadrant 4. We could add like another pi to this and then subtract off part, but I think the easier way is if we take our answer, add 2 pi, go all the way around, then subtract off our answer to get back here. So I'm going to do 2 pi minus our answer, our positive answer. So in this, it gives us about 5.3559.
All right. This one's pretty fun. So now we're actually finally solving an equation. So W. It just wants us to find all the solutions of x that will make this equation equal 0. So first, I always recommend writing everything in terms of sine and cosine. So I guess we're going to do that step second, because first, I noticed that there's a 2 right here. And so I'm actually going to divide by 2 everywhere, and 0 over 2 equals 0. So we can just kind of get rid of that 2, and then I'm going to rewrite the expression. I know that cotangent is the inverse of tangent, which means that it is cosine of x over sine of x. Okay? Plus sine of x minus 1. Excuse me. All right, equals 0. Then, let me just kind of simplify this out even a little bit more. So we're going to have cosine squared x on the top over a sine of x plus sine of x right here minus 1 equals 0. I'm going to multiply both sides of my equation by sine, which will lead me to having cosine, so I can get rid of that fraction right here. So that'll leave me to have cosine squared x plus sine squared of x minus sine of x equals 0. And like we previously went over, this is the Pythagorean identity, so this actually equals 1. So then rearranging my equation, since I have 1 minus sine of x equals 0, I can say sine of x, by moving it to the other side of the equation, equals 1. Now, this is a lot more manageable to solve. We take the inverse sine of both sides to get our angle, which equals, on the interval of 0 and 4 pi, inverse sine of 1 is pi over 2, and 5 pi over 2, right? Mm-hmm. Yeah. And 5 pi over 2. Sure.
Last problem, we're almost done. Okay, here's another solving an equation. So, looking at this, I again want to get all of the x's to one side. So, but before I do that, I have a cosine of 2x in here, which is a little annoying, so I want to use the identity that cosine of 2x equals 2 cosine squared of x minus 1. So I'm going to rewrite that as 3 times 2 cosine squared of x minus 1, and then plus 2 equals 2 cosine squared of x. Okay, now I'm going to multiply this 3 out to get 6 cosine squared of x. Then we have minus 3 plus 2, so that's minus 1. equals 2 cosine squared of x. Okay, and then these are like terms, they're both cosine squared, so I can move them together. So I'm going to subtract 2 cosine squared of x from both sides. You get 4 cosine squared of x minus 1 equals 0. Okay, and then I can add this 1 over to get 4 cosine squared of x equals 1. I want to get rid of this squared, so I'm going to square root everything to get 2 cosine of x equals plus or minus 1. Okay, and then divide everything by 2. Cosine of x equals plus or minus 1/2. Okay, now we need to check our interval. So we have 0 to 4 pi. That's twice around the unit circle. So in our unit circle, cosine equals 1/2 here, negative 1/2 here, negative 1/2 there, and 1/2 there. And that is at ones that's pi over 3. This one is 2 pi over 3. This one is 4 pi over 3. And this one is 5 pi over 3. So it's all the thirds, really. Okay, and we need to do that around the circle twice. So our solution has all of those, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And then instead of trying to figure each one out, because we're just going around the circle again, it's just we can add 2 pi to all of these. And 2 pi is the same thing as 6 pi over 3 to get that common denominator. So then we have 7 pi over 3, 8 pi over 3, 10 pi over 3, and 11 pi over 3. Lots of solutions. Cool. Thanks for watching, everyone.